Hey everybody, welcome to today's video about polar and non-polar molecules. I'd like us to start by remembering what we said in an earlier lesson about polarity of bonds. When we're studying a bond between two atoms, it's really about the difference in the electronegativities of the two atoms that determines if the bond is polar or not. So if you recall, we said that if that difference between electronegativities is really great, then what we probably have there is an ionic bond between cation and anion. And remember that when cation and anions attract to each other, they do so in such a way that the cation attracts the anion, which attracts another cation to an anion, and the structure grows into what we call a crystal lattice. So it's a big aggregate of cations and anions, and it does not exist as discrete molecules. So for today, we're just going to ignore those. Okay, we're not interested in those. Today, instead, we're looking specifically at collections of nonmetal atoms which are sharing electron pairs in covalent bonds. So let's look at the difference between a polar covalent bond and a nonpolar covalent bond. We said that a polar covalent bond is recognizable if you just watch out for a funcle, for fluorine, oxygen, nitrogen, or chlorine as one of the atoms in the bond, and then the other atom is not one of these. Okay, if that is the case, even without a table of electronegativity values, you can conceptually understand that your bond will be skewed. The electron density will be skewed toward the more electronegative atom, and we will label that bond as a polar bond. On the other hand, if your two atoms in the covalent bond are the same atom, or if they have very, very similar electronegativities, like carbon and hydrogen do, then the bond between those is, an example of equal sharing of electron density, and we call that a nonpolar bond. All right, so let's start by considering two really simple molecules. The O2 molecule is made of only two atoms, and the hydrogen chloride molecule is made of only two atoms. Now, whenever your molecule is simply two atoms, it has to have a linear geometry. The only way to connect 2 points is with a line. So these are both linear molecules, and the polarity of the bond is also going to tell you the polarity of the molecule. This is a nonpolar bond, and so the molecule is nonpolar. And on the other hand, hydrogen chloride, the bond between those is not evenly distributed. The electron charge is skewed toward the more electronegative atom. This that I've drawn here is called a bond dipole, and it's always pointing toward where the electron density is greatest. So this bond is a polar bond, and this molecule is a polar molecule. We're going to be looking for polar molecules as those which have an unequal distribution of charge around the molecule as a whole. Okay, now these are two really simple molecules because they just have two atoms and one bond between them. Let's now turn our focus to more complicated molecules, starting with molecules that have three atoms. So if you have three atoms, then you have more than one bond. This is carbon dioxide, and you'll remember when we did our marshmallow models that it looked like this. So considering the central atom has only two electron domains. Let's just review. An electron domain is either a single bond, or it's a lone pair, or an electron domain is also a double bond or a triple bond. So one domain, two domains. And Vesper theory tells us that when you have two electron domains around the central atom, they are going to get as far apart from each other as possible, minimize the repulsion with a linear geometry and 180-degree bond angles. Now, the two bonds, the carbon to oxygen bond here, looks like this. So we have our bond dipole pointing toward the more electronegative oxygen, and the same thing here, pointing toward the oxygen. These two bond dipoles have the same magnitude, but can you see that they are diametrically opposed? Okay, they are pointing in exactly the opposite direction from each other. When that happens, we say that the bond dipoles cancel. So these both have some magnitude, but they're pointing in exactly opposite directions. And when bond dipoles cancel out, then we say that the molecule has zero dipole moment. Okay, let's talk about this term dipole moment for just a moment. Dipole moment is really more of a physics quantity. If you take physics, you'll probably learn how to calculate this. It does have a number value, but it's effectively the net sum of the vectors. So if you haven't learned about vectors yet, vectors have a magnitude and a direction. If the two vectors have the same number value, but opposite directions, then they cancel each other out and the net dipole moment is zero. Okay, that's what's happening in this molecule. Okay, now let's look at another molecule. This is actually a polyatomic ion. This is thiocyanate. It again has carbon in the middle and two electron domains. So it's another linear geometry, this time a single and a triple, but these are each an electron domain. But what's different here is that the bond dipoles are not identical. So if I represent again the carbon-oxygen bond dipole like this, the carbon-nitrogen bond dipole also points toward the more electronegative atom, but it has a different magnitude. Carbon to nitrogen has a different bond dipole than carbon to oxygen. These two bond dipoles are pointing in opposite directions. They're 180 degrees apart, but they don't have the same magnitude. So this is a case in which the dipole moment of the molecule is not zero. The dipole moment, the net sum of these two vectors doesn't equal zero. So non-zero dipole moment, where dipole moment is in effect the net sum of the vectors. This molecule is lopsided. It's a polar molecule. So we're going to think of polar molecules as being lopsided in their distribution of charge. And we're going to think of non-polar molecules as being not lopsided. Okay, let's consider another molecule. Let's look at boron trifluoride. So when you do an electron dot diagram, a Lewis structure, a Lewis electron dot diagram, it looks like this on paper. And on paper, this looks like a T-shaped molecule. But remember, when you consider the central atom and you're counting how many electron domains, we come up with 3. And we learned that 3 electron domains will minimize repulsion by maximizing their bond angle, 3 120-degree bond angles. This geometry is called Trigonal Planar. And the bond dipoles, each one is showing the skewing of electron density toward the fluorine, the more electronegative atom. So we have three identical bond dipoles here. The three bonds are the same. Because this molecule is planar, it's flat as a piece of paper, and the three bond dipoles are the same, and they're all arranged symmetrically on this plane, then these three bond dipoles do in fact cancel each other out. That's a little harder to see than when we had linear, just two pointing in the opposite directions. This is three bond dipoles, all equal distance from each other on a plane. This molecule has a 0 dipole moment. The bond dipoles cancel out. The net effect is 0. Let's take a look at the sulfur dioxide molecule. Now, we did this one in an earlier lesson. The Lewis electron dot diagram looks like this or like this. And when you assign formal charges, you see that one structure is not preferred over the other. The formal charges are the same, however you draw it. So that is an indication of resonance. Neither of these structures is actually correct. The true value is a blend of the two. But in either case, our central atom has 3 electron domains. Again, remember guys, an electron domain can be a single bond, it can be a lone pair, or it can be a multiple bond. So 3 electron domains around the central atom, and that looks like this, with again the 120 degrees between each. But in this particular molecule, 2 of the electron domains are bonds, and 1 electron domain is a lone pair. Now the bond dipole is S2O. So I have a bond dipole of sulfur to oxygen, electron density skewed toward the more electronegative oxygen, and then over here, sulfur to oxygen again. So we have 2 equal bond dipoles, but they are not diametrically opposed. They're not 180 degrees apart. And furthermore, we have an electron pair here that belongs exclusively to the central atom. So that's another area of electron density, and it does not have a balance on the opposite side. This molecule is lopsided. It is polar. It has an unequal distribution of charge around the molecule. It has a net dipole moment that's not 0. And so this is another example of a polar molecule. And in fact, anytime you have 1 lone pair on the central atom, the molecule has to be polar. If you have 1 lone pair on the central and it's not balanced by another lone pair on the opposite side, it has to be polar. Okay, let's look at yet another. Let's look at ammonia. The Lewis electron dot diagram makes it look like it's T-shaped, but when you consider your central atom, you see that it has 4 electron domains, 1, 2, 3, 4, and 4 electron domains means that we have a tetrahedral geometry. So here is ammonia. 4 electron domains. This is not planar. This is not flat on the paper anymore. So this is a 3-dimensional structure with 3 of the domains being bonds and 1 domain being the lone pair. Now these 3 bonds The bond dipoles are all the same magnitude, but they are all pointing up in space toward the central atom. Remember, this geometry of the molecule is a pyramid. So the bond dipoles are not canceling out, and even more important, the central atom has one lone pair, which tells us it must be a polar molecule that has a non-zero dipole moment. Okay, now let's look at water, H2O. When you draw the Lewis electron dot diagram for water, it looks really balanced, doesn't it? It looks linear, it looks nice and symmetrical, but be careful, guys. Your central atom has 1, 2, 3, 4 electron domains, and that means a tetrahedral geometry of those electron domains. So here's water. This is not planar. This is a 3D structure. 2 of my domains are bonds, and 2 of the domains are lone pairs. These 2 bonds have bond dipoles that point toward the oxygen. Okay, they do not cancel each other out. And then we have 2 lone pairs, but they are not opposite of each other. They're next to each other. So this molecule, water, is most definitely a polar molecule. Now, you really need to get that one fixed in your memory. Okay, it is so easy to draw a Lewis structure for water and say, oh, it's so nice and even and balanced, it must be nonpolar. Water is a polar molecule. So many reactions happen in a water environment, and so many solutes will dissolve in water solvent that this guy is just super important to us in chemistry. The geometry of the molecule is bent. The 2 lone pairs on the central are next to each other. They don't cancel, and the 2 bond dipoles do not cancel. Polar molecule for water. All right, now let's take a look at carbon tetrachloride, CCl4. Here's our Lewis electron dot diagram. The central atom has 4 domains, so we think about the tetrahedral arrangement of those domains. And in this case, each of the 4 domains is a bond. The bonds are all the same. They are all polar bonds with the electron density skewed toward the chlorines. Now this one, in the past I've had students who just really struggle to see this, but in a tetrahedral arrangement, if all of the bonds are polar, because they're all 109.5 degrees apart, the bond dipoles do cancel. And this tetrahedral molecule with 4 polar bonds ends up having 0 dipole moment. The 4 bond dipoles cancel, and this guy is a non-polar molecule. But now let's consider CH2Cl2. Okay, here's our Lewis electron dot diagram. It has a tetrahedral geometry. And see the way we drew it on paper, it sure does look like these 2 polar bonds are opposite each other and would cancel. And it looks like these 2 non-polar bonds are opposite each other and would cancel. That is not in fact the case. Okay, so let's just look at this tetrahedron. Now it looks like if these 2 bonds were the polar bonds, it looks like they are opposite of each other, doesn't it? But watch, hold on to them. See, they're actually side by side. And these 2 bonds right here, if these were my nonpolars, And I say, yeah, they look like they're opposite of each other, but just look. They're not. They're side by side. In a tetrahedral arrangement, you really can't get two of the domains opposite of each other. No matter which two you pick, I promise you they're side by side. If you are struggling to see that, please get some marshmallows and toothpicks and play with that yourself. So this molecule is lopsided. It has an unequal distribution of charge around the molecule. Okay, the last one I want to talk about, let's add this to our list. Whenever you have two lone pairs on a central atom, I should have said that when we were talking about water. Here's water. Whenever you have two lone pairs on the central atom, if the lone pairs are side by side, then you have an unequal distribution of charge. You have a polar molecule. But I want to contrast that with this structure. Do you remember this one? That came from having 6 electron domains on the central. When you have 6 electron domains, if you put 4 electron domains as bonds around the equator and your 2 lone pairs on the axial position, this is an instance where your 2 lone pairs are 180 degrees apart. They are across from each other. So that's a case of 2 lone pairs on the central, and the 2 lone pairs do cancel out. This is a case of 2 lone pairs on the central, but the lone pairs are side by side, and they don't cancel out. Okay, so again, guys, that was a lot. As you're going through all of the practice that I'm going to give you, you want to, first of all, examine the bonds within the molecule. And if the bonds are polar bonds, then you have to decide if the bond dipoles cancel each other out, thereby giving a 0 dipole moment, or do the bond dipoles not cancel out and the molecule has a non-zero dipole moment. Also remember to look at lone pairs. If there's only one lone pair on the central, it has to be a polar molecule. If there's 2 lone pairs on the central, it's all about, are they side by side or are they diametrically across from each other? Okay, guys, thanks for paying attention to that and good luck with the practice.